Okay, so this talk is going to be about the Spivak normal fibration. So I guess we're almost sort of in a position to start talking about some of the sort of major successes of surgery. So remember we first asked the questions, when is one manifold homotopic to another? And the other question is, when is one manifold diffeomorphic to another? So using the H and S cobordism theorems, we can reduce the second question to when is one manifold H cobordant, or in the case of non-simply connected, S cobordant to another. Browder, Novikov, Sullivan and Wall formulated a systematic sort of approach to this problem. But to understand their approach, we're going to have to start talking about a kind of auxiliary question. So the question this talk is going to be concerned with is question: when is a finite CW complex homotopic to a manifold? Closed, I guess. So this is sort of going to be, I guess, a kind of change in focus over the next few lectures to try and answer this question in a systematic way. And using the language that we'll develop, we'll hopefully be able to try and answer the other questions that we were talking about before. So for instance, if you want to show that two manifolds are H cobordant, you might want to find a cobordism between them and do surgery on that cobordism to try and make it an H cobordism. But the instructions to doing so, well, we can find using the tools that we're about to develop. Okay. So another theme of this talk is going to be the difference between fiber bundles in general and vector bundles. So on one side you've got homotopy theory, theoretic objects, and the other side more traditional like objects of topology. Okay, so section 1 is going to be Poincare duality. So I guess the first thing you might say for this question is manifolds have Poincare duality, and homotopy preserves this property. So our CW complexes better have Poincare duality. So recall from Spiros's talks that we have a chain complex of Z pi modules associated to our so X is going to be a CW complex. CW complex. Let's say finite CW complex. So it's possibly non-orientable. So we have this object that's for us to find the orientation character, which is a representation of the fundamental group here. So using this, we can define the chain complex twisted by the representation. So what I want to say here, H star. That? No, I want to do the lower one. This. And then taking the homology of the chain complex, this should define something, so taking the nth homology. This should define the homology with twisted coefficients. So that's there, of the CW complex. Okay, so definition. Okay, so a connected m-dimensional There's a lot of words here. Geometric Poincare complex. So this is what I'm defining. Or, as I will refer to it in the future, a P-space. Okay, so is a connected, let's say, finitely generated CW complex. So it's a connected, so finitely gen CW complex. So we want to give it Poincare duality. So we say it has an orientation character. So do I? Okay. So with orientation character, which is a map here again. Okay, and fundamental class. So this should all be very familiar. I'm mimicking the properties of Poincare duality in a manifold. So fundamental class is some class that is in the nth homology of X with twisted coefficients. And the class has to give a Z-pi chain map. By capping. So this should be a map from this Z-pi chain module to this one. That is a so Z-pi chain homotopy. Okay, so these are the objects we're going to be looking at in this talk. Equivalence, I guess. Yeah. Okay, so remarks. So this gives us an isomorphism on, well, on the level of homology slash cohomology. So this induces so what have I gone for? N minus okay, so this is going to give us a number of isomorphisms because of the twisted coefficients. So if we start off with twisted coefficients, it's going to give us an isomorphism to the untwisted case. And vice versa. So passing through this sort of twisted Poincare duality is going to twist or untwist your coefficients depending where you started. Yeah, so I might say that as well. Just for completeness, so let's say we start off with, and this is going to be an isomorphism to start with twisted coefficients. Okay, so usually I'll drop the Z if it's just in the integers. Okay, so another important thing that we're going to use quite a lot is that this works for CW pairs. So I'm not going to run through the whole thing again, but so the changes we need to make are now that the fundamental class, sometimes this is written relative to the other part of the CW pair. so my CW pair is going to be x boundary of x, suggestively. I mean, it doesn't necessarily have to be a boundary because it doesn't quite make sense in the language of CW, but this is what I'll call it. So this is going to belong to the relative. Oh, do I want that? Yes. So it's going to belong to the relative homology here. Again, with twisted coefficients. So we're going to get, for example, so e.g. we get, oh, I don't know, so something like, so it's going to give us, so this will be capping with the class. So this is going to give us some kind of Poincare-Lefschetz duality. So H star, let's say X, and now I don't want to twist the coefficients. Did I want this? Maybe I wanted these all to be the universal covers of these objects. Okay, it works for both. So the way I've stated it, this is on universal covers, but you can always pass down to the actual cohomology by, again, twisting your Z pi chains with representation Z pi.